limitation of convolutional neural networks, and one of them is explainability. So we can see that the model can highlight area of the scan with a certain probability of a cancer. By why is this area? What led the model to select this area? It's very hard to tell. Another limitation is the debugging. So debugging of wrongly segmented organ. So why the model chose these voxels to belong to the organ, and where in the model are the weights that led to this wrong decision, and what are the training examples we need to fix that issue. Another limitation is the training data. CNNs need a large amount of annotated training examples to achieve high accuracy, while in contrast with natural images or text data, there are no large data sets of expert annotated training examples in medical imaging. Another limitation is the retraining. So CNNs lose information during retraining on updated data sets. So we have already trained our model to recognize and segment certain organs. We add more examples, we think we will get better, but we will not. Because the model after retraining actually forgets what it learned before, thanks to the retraining. Another limitation is stability. CNNs are highly susceptible to butterfly effect. A small variation in input data can lead to drastically different results, making them inherently unstable. Another limitation is that all the filters or kernels in the CNNs that perform convolutions are squares or cubes. This works well for natural images, but it's not ideal for medical imaging. So we knew these limitations, and we developed the graph model. And it has several steps that are taken. And the first step is supervoxel oversegmentation, that is performed on all available modalities, on all scans. And it would look like this. This is in 2D. So you can see all these areas, which we call supervoxels. This is on MR, magnetic resonance. This is on a CT. So also these modalities are very different. It's the same patient, and the structure of these stones are similar. And this is how it looks like in 3D. So the third step, well, let's say the second step, the algorithm finds features of each supervoxel, such as smoothness, size, shape, pattern, homogeneity, and many more. We can see it here. So each of them has its own parameters, which we will use. And then we create a common graph for all available modalities of the patient. So each supervoxel is represented as a node of the graph, like this. And these are the edges which connect these nodes. If I'm going back to the example, this is a single supervoxel, and these are the neighbors. So they will be connected to it. And then the fourth step will be that embeddings of all nodes are calculated based on normalized features of each supervoxel. So the embedding is similar like an NLP, where we look for words that are in the corpus next to each other, and that would be the embedding. So we don't look just at the parameters of each node, but we look at the neighbors because we want to understand the structure, not just the actual features of that node. The trained graph model loads prepared graph of the patient and calculates labels for each node that represents supervoxels. So we can see it like here. So we can display certain features of each supervoxel. And then we can create a label. For example, for this one, it would be a bone, and this would be I think it's bladder. So now we can see it all the 3D like this. Then afterwards, transformation matrices among the labeled organs and tissues are calculated for all modalities, CT, MR, ultrasound, PET, SPECT, for all the scans. And labeled, co-registered, and processed scans are prepared for visualization. So how have we done the test? The scope of the test, we have quantitatively and qualitatively compared 3D segmentation of the most popular CNNs, architectures, against deep graph model. We done it on CT, T2 MRI, and ultrasounds. So these architectures included UNet 3D, dense VNet, ScaleNet, high-res 3D net, Deep Medic, Holistic Net, and VNet. We have trained all models on a single GPU with 11 gigs of memory for CNNs and 8 gig limit for deep graph model. We set optimal hyperparameters for all models, such as learning rate, augmentation, and many others. And we had to train separate models for each modality for CNNs, architectures. Deep graph model is trained on all modalities in the same time, but because of the validation error is different for different modalities, we show them separately. All the models were trained until the validation error plateau, and segmented volumes include rectum, bladder, prostate, bones, cancerous lesion, and iodine seeds for treatment of cancer. But not all modalities allow segmentation of all organs, and all scans were normalized using default settings for all architectures. And now this is the data set, which is for MRI of pelvis scans. We had 100 training examples, 50 validation. For CT, we have 73 training, 25 validation. For ultrasound, 55 training, 15 validation. As you can see, it's rather small numbers because there is really not a large data sets of these annotated scans. And when you compare it with natural images, you get millions and tens of millions of examples. That's not the case for the medical imaging. So this is the result. So we can see that the best from the convolutional neural network is a VNet for our purpose. This is the validation error on CT scans, validation error of MRIs, validation error on ultrasound, and deep graph model is the best here. Now we go a little bit into the details, which are qualitative analysis of the issues where we've seen on CNNs but not on DGM. Now, features with small intensity differences were ignored. So an example are tips of the prostate on MR, magnetic resonance. So these features can be distinguished by human and correctly segmented, but CNNs fail to include them. So as you can see, this is what the CNN returned to us and then around that fuzzy area, this is the actual prostate. That is not correct. Second one, it's thin walls of hollow organs, such as rectum or bladder, when often not fully segmented. So it looks like thin features under 8 voxels are often invisible for CNNs. This can be related to the size of the cube-shaped filters in lower layers of CNNs, and you can see these holes in here. Another issue is averaging between training examples of organs with variable sizes. So we had the training examples with segmented bladder, and a portion of these examples had a full bladder and portion empty. Now, we have seen some validation segmentation capturing only part of the bladder. So it looks like CNN's average size of the organs, which is very undesirable. This issue cannot be fully mitigated by the increased number of training examples. So even when we put more training examples with full bladder and empty bladder, we can still see this issue. So we suspect that the higher layers of CNN filters cannot hold alternative strategies of single organ segmentations. Now, small features disappear from segmentations. So, in order to perform comprehensive segmentation of the scans, we need to distinguish organs, tissues, and lesions from 1500 cubic centimeters to 0.1 cubic centimeters. So we have seen many validation examples where the lesion under half cubic centimeter were not segmented at all. So this probably is caused by medium layers of CNN filters and pooling, where only the largest features are propagated to higher layers of the filters. Another issue is segmentation is next to the intensity border instead directly on it. It's likely to be caused by size of the lowest layer cube filters in CNNs. So variable shape CNN filters should solve this issue, but our CNN architectures and implementation did not have them. So you can see the actual bladder should end here, not next to it. Another issue which looks funny, but this is a spillage of segmentation to neighboring organs. So this issue is triggered by combination of fuzzy border here between organs and similar pattern and intensity of neighboring organs. Now, none of the CNN implementation is aware of location of the filter during segmentation process. So essentially the filter is scanning all through that scan, but we find some is not aware of location. So this causes that part of the rectum, like in here, this can be segmented as a prostate, even if it's anatomically in different position. So the CNN cannot deal with anatomy. Now, misidentification of tissue and organs. So this issue appears in MR scans with lower resolution and lower intensity ranges, and it is caused by over-reliance of intensity of the voxels. So CNNs are not aware of anatomy of the scan and try to use intensity and pattern in order to segment given organ, and that's not always possible. So the first application of deep graph model is Dynocortex for prostate brachytherapy, and we have demonstrated superiority of the approach compared to traditional convolutional neural network by creating a single view of the prostate area from CT, MR, ultrasound, PET-CT scans, segmentation of organs of interest, automatic co-registration towards root scan, and identification of small iron seeds used for brachytherapy. Okay. So in the past I use graph neural networks for fields like finance and LiDAR processing. And after discussion with medical imaging expert Roll Moore, we saw the limitation of convolutional neural network and advantages that graph neural network give us, and we found Dynocortex in early 2016. Now I would like to show you how it looks like in practice. So the software runs inside 3D slicer. We can choose a root scan, which is a CT scan. And the word registration means essentially that the scanners have different sizes, but we want to have all the different modalities like ultrasound, CT, MRI moved to the single 3D volume, so we can see how the organs look like on all these modalities, so we can tell difference where we have, let's say, inflammation, where we have cancerous lesion, where we have scarring. If we see only one modality, we cannot tell it. We can often not tell it. So here, what I do, I set some root scan, which is here, the CT scan. Then I choose MR scan and PET scans, and here ultrasound. If we have more, it will select more and let it compute. So what is going on now? It's computing segmentations for all the organs. Just a second, I started. It was a little bit slow, so I restarted it. Here we are. So we choose some patient in here and we choose some scan. This is the root scan. And here we can choose the other scans which will be co-registered. So now we run the actual segmentation. And then we use the segmentation in order to register and put them on the same volume. And then I can show you how it looks like to the end user. Okay, here we are. So what we see here, this is a CT scan volume, and these are iodine seeds that are used for treatment of prostate cancer. Here we can see the whole scan, so these are the outline of bones on the CT. And yes, please. 5 minutes, okay. With question or without questions? All right. So here we can see the segmentation of the organs. But what we wanted to see that they are correctly registered. So this is the blue line is segmentation of the bones on the CT. The green is segmentation of the bones on MR. And that one is on the CT, belong to PET CT. And if we put them all together, we see they are on the same volume. That's what we wanted. That's the first. Now, we can take a look at the prostate area, switch off the segmentation of the bones. and we can switch on CT, switch on the bladder. So this is the bladder. Okay, this would be rectum. I can see that. This is on a CT. When we switch modality in here, this is done on MR, and that in the middle, that is a prostate. And this is a PET CT. So, and this is ultrasound. So now it's on the same, so this segmentation comes from MR, the volume comes from the ultrasound, and these dots are fiducials, they come from the CT. So we have all these modalities together. Now I switch towards PET CT, and that shadow is the PET modality. Okay, now any questions? Yes, please.
It's a two-part question. The first part is, how far pronounced must the cancer have been for this method to be able to detect it as opposed to traditional methods?
So our measure is always to be as good as a doctor, but this is a tool for the doctors. So there's lots of routine work that is currently done manually, which is, as you see in the segmentation, and registration, which is moved manually, and calculation of doses and so on, which is like a dose volume histogram. But we try to be as precise as the person, as the doctor. But all the software is meant to be a tool, so it's not replacement for a doctor. It's a tool, so essentially if the software claims that there is a lesion, so the doctor has to come up and make sure that's the case. The advantage is he can see it together with minimal effort in multiple modalities on the same volume. So it makes much easier. So you can see it in 3D and 2D on the same space like this. So this is the prostate. This is from ultrasound. This is prostate again on MR. This is a prostate on the CT. And so it's very easy to see it. And obviously 2D and 3D. So that's.
So is there a constant feedback in the doctor, and is that how the model is trained? Because you mentioned that the model is trained in a sort of NLP format.
Yeah.
Therefore, it would be prone to. In NLP, you have things in a grammatical sense, such as my favorite number in the whole alphabet is blue, sort of thing. How would you correct for such discrepancies? Is that the doctor feedback that you get in response to
So feedback is done this way, that the system proposes you a segmentations, finds you the lesions, put these red fiducials on it, and all sorts of things. Now, the human must verify that that's the case. Now, you can manually adjust things. So if I go to to the MR and I can decide, okay, I don't like the segmentation, I can, do they call it contouring. I can make changes. So I think, this is not a part of the segmentation, or all this bit is part of the segmentation, so I can actually adjust it and then recalculate it. So I have, as a human, I have the last word, what is true and what is not true. Then this is a corrected example, and that will be used for the training. So this is the feedback. It's not direct feedback, but it's feedback after a human makes the changes. Yes, please.
So each of your imaging modalities is taken at a different time. Is that going to, and obviously the body changes over time.
Correct, and that's...
Would there be a real limitation for this technique?
Well, that is true. For example, with the bladder or with the rectum, it's changing by the hour, by the minute, and it's difficult. But that's why we need tools like this, where we can do this registration automatically, and we can deal with the movements of the organs. And so, if I can cancel this, but essentially, if I'm coming here, there is a registration which is on the bones. Okay, I'll put some other patient here. This one. There's a registration on the bones, which is a rough registration. Doesn't take into the account the movement of the organs. It's just on the bones in the pelvis area. But for example, you got a rectum and bladder, and they actually move. And in the middle, there is a prostate. So the prostate is moving, is pushed by the bladder and by the rectum. And we actually take that into the account. Yeah, it's a very good question. I can even show you the movement in a second. Yes, please.
Come back to the first question. Can you explain what you're hoping to achieve in terms of the clinical outcome for the patient? It's not diagnosis. I know it. I mean,
okay.
I think it's maybe people don't realise why you're trying to do this.
So the first thing, and the most important bit, and we were asked to do so, it's a quality assurance. So we want to make sure that these iodine seeds were correctly implanted, and that's why we have something which is called dose volume histogram, which tells us how much of the organs is hit by the radiation. So if I switch on the radiation, which are the isodoses, and then switch on the prostate, so we can see how much of the prostate received the therapeutic dose. Now, if I switch on the contouring of the rectum, and we can take a look, and you can see inside the rectum in the wall how much is hit by the radiation from these iodine seeds. Now, if it's hit too much, it means that the patient will be in lots of trouble. The same is on this side, where I want to take a look at the bladder, and again I can see how much the bladder is hit by the radiation. What happened is that if the whole prostate is not properly covered by these iodine seeds, the patient needs to be reimplanted. So they have to put more seeds in the area that are cold, that they didn't receive enough radiation. So this is the main purpose. And then obviously it can be used for planning where I put those seeds, because I have now all the modalities available, so I can make decision, because there are inside, if we can take a look, inside I switch off the isodoses. As you can see, this one is the urethra, where the urine is sort of moving, and those iodine seeds must not be placed next to the urethra. So this is another thing. So there's lots of clinical advantages to have those data available. Good question. Another question?